Hello, and welcome back to this video series in which I cover the basic steps needed to build mini simulations. I am focusing on the corona discharge example. So if we continue working on this generic simulation that I've set up, you can open the field dynamics option. You can expand that. And then there's this option called field boundary conditions. For the electrostatic field solve, you need to, there are no default boundary conditions. So if I right click here, you can see there's two options. There's Dirichlet and Neumann. A Dirichlet boundary condition is one in which you specify the potential, and a Neumann boundary condition is one in which you specify the derivative of the potential, which is the electric field. So a Neumann boundary condition is one where you specify the electric field. So for a 3D simulation, we will need a minimum of 6 boundary conditions to establish the boundary conditions on the boundaries of the simulation domain. So if I right click here, I'll just do this 6 times. Okay, so 1, 2, 3, 4, 5, 6. I like to rename them. So this is Dirichlet 8. So I'm going to call this Dirichlet upper X or lower X. So this will be the boundary condition for the lower X surface. Upper X, and you can do that for the rest. That way I know I have all my bases covered. So I'll need a lower X, lower Y, lower Z, upper Z. And now you have to select the surface. So this will be lower X. Let me just quickly point out that you can do partial boundary conditions. So for example, I could do this partial lower partial upper X here, and if you do that, then you have to specify where what the Y and Z coordinates are for the location that the potential will be specified. I would then have to do another partial boundary condition on the upper X in order to get the entire boundary condition for the entire upper X surface. So you can do what are called partial or mixed boundary conditions, and this could be partial Dirichlet, and then another part of it could be Neumann. Now you can also specify these as space-time functions. So if I went up to the space-time function option, right-click, add an expression, then I could specify a time-dependent potential. Let's say it's 30 volts. Oops, got ahead of myself there. We'll call this the RF potential, and we'll put the expression down here. 30 volts times sine of omega times t. Now I've hard-coded in these constants, and of course you could come up here, create a constant called V naught, and we will let that be 30 volts. Create another constant called omega, and that will be 1,000,000. And then now we could put in the constants here. Oops. Okay, and then you could come down here, and I could specify this by right-clicking here, and then I specify my RF potential. Now I have a time-dependent potential established on the lower X boundary condition. So let's see how this is done in the example, on the corona discharge example. So we expand the field dynamics option, and you can see I've got Dirichlet boundary conditions, Dirichlet lower and upper y. So this is my lower y down here in this region. And then my upper y is up here. And then the other four boundaries are the z and the x. I set lower x, upper x, lower z, and upper z as Neumann boundary conditions. And the reason is because I want the plasma to determine the potential when corona discharge occurs. If I set lower x, upper x, and lower z and upper z as Dirichlet boundaries, then I would be specifying the potential, and the potential would really be governed by the boundary conditions and not the plasma. So a good way to have what are called floating potentials is to use Neumann boundary conditions. And in doing so, you will find that the plasma potential dominates the physics. And that's what we need for this problem. Then I have two more boundary conditions. I've got the sphere and the outer cylinder. So this is the sphere here. So if we go back to geometries and I click on sphere, then there's my sphere. And then the top boundary is a conductor, and within that conductor is the dielectric. You do not specify the potential of a dielectric. You specify the potential only of conductors. The electric field and the potential in the dielectric are self-consistently computed, and I'll show you how that's done in a minute. So now I've got the sphere, the Dirichlet sphere, and I set that to 0 volts. Or sorry, I set that to 0 volts. And then the top boundary, I set that to delta sub V. The way I computed delta sub V is through using Poisson's equations and Poisson's curve. So if we go here, this is Poisson's curve. This is voltage versus pressure times distance. I found a paper, Hussein and Nima, from August 1992 here. I found an equation using Poisson's results, which you can read through, and I used that in this example to determine the potential difference given for this distance. So let me go ahead and remove the grid. And so there's some distance between here and here at some pressure. So given this distance and given this pressure, Poisson's curve predicts that there will be corona discharge for a given voltage. And I used that voltage that I computed from that equation in this example. So that voltage is just set up as a constant here, 923 volts. Okay, so that is the potential that I put for this top boundary here. Now, I could have set that up. I could have actually coded all of that up in this example also. So you could do that. You could set that up as a parameter, really. So that could be a exercise for the user. Okay, now that I have all those boundary conditions established, so I have 8 boundary conditions, 6 for the simulation domain, 2 for the geometries. Let me just actually point out one thing. So if you look at the grid again, you'll notice that the grid goes through the top part of this geometry. That's actually a good idea. You want geometries to poke through the grids. You don't want them to overlap. You get a better performance if the two do not overlap. And that's why you see these geometries sticking out. For one thing, I don't need this whole sphere. I only needed the top part of the sphere. So that saved me in computational time. And so the boundary conditions on the lower y and on this sphere are identical. They're both 0 volts. They have to be physically. They are touching. So two conductors that touch will be at the same potential. Likewise, the potential of this cylinder on the top and this top y boundary condition or upper y boundary condition are also the same. So if you go here, expand this, Dirichlet outer cylinder is delta sub v, Dirichlet upper y is also delta sub v. Now how did I include the dielectric? Well, let me go over how the electric field and the potential are solved for in VSim. So in VSim, the way we solve for the self-consistent electric field is through Poisson's equation, which is this top equation here. Del squared phi equals minus rho over epsilon naught. Rho is the charge density which is found by weighting the particles onto the grid. Phi is the electrostatic potential. In VSim, del squared is converted into a matrix, I'll call that capital M, using standard second-order finite difference methods, which creates the stencil. So we've converted this differential equation into a linear algebra equation, and we have an equation m times phi, where m is a matrix, phi is now a vector, equals minus rho over epsilon naught. We invert this to solve for phi. Now, inverting this matrix M directly in 3D is not possible. The matrix is simply too large. So VSim uses iterative methods. We do have direct methods that can be used for 1D and smaller 2D problems. But you'll notice here, this is the part I also want to get to, is there's this epsilon naught term. Epsilon naught is the permittivity in free space. But we actually need epsilon as a function of x, y, and z, since we have dielectrics. So in my example, epsilon of x, y, and z is my space-time function, perm cylinder. So if we go back, and we just expand here, perm cylinder, this would be epsilon as a function of x, y, and z in Poisson's equation. Where we put that is if we expand the field dynamics option, then we see there's a Poisson solver option right here, and then there's relative permittivity, and I right click, and that's where I include my space-time function. Okay, and we went over sort of the anatomy of that space-time function in the last video, or maybe it was video number 2. Okay, so now we have set up the electric field, the solver, and the boundary conditions. Let's just quickly go over some histories that I've put in this simulation. I like to keep track of the total number of particles. So if you histories is a way to collect special kinds of data in the simulation domain, and they're very efficient. So for example, collecting all the particle data takes a lot of hard drive space. But if I just wanted to know the number of particles that hit some surface, then I could use a history. So if I right click, then one of the histories is called number of macro particles. So here, that's what I'm doing. I'm keeping track of the number of secondary electrons and the number of nitrogen ions. So that's just number of macro particles. Another history you could do is I could do a log history, and I like to do absorbed particle log. But to do that, you actually have to set up a absorb and save boundary condition, which I did last time. So for all of these, I'd set the nitrogen up as an accumulate boundary. That's a special kind of absorb and save. So then I'm going to collect all of the nitrogen that accumulates onto the dielectric, and the data that I'm going to save, I'm going to log per particle. So when each particle hits it, I'm going to collect a certain type of data. To get that data, I need to right click here, and I need to add a particle quantity. So I'm going to collect when the particle hits. I'm going to collect the position. I have to do that 3 times because it's a 3-dimensional simulation. So I clicked on position 3 times. I'm going to collect position 0, position 1 and position 2. That's just the x, y, and z positions. Same with velocity. I have to do that 3 times. And you could keep doing this for other quantities too, such as the energy, the weight of the particle, etc. So this says that every time a nitrogen ion hits that dielectric, I'm going to save this data. Now, the only way I can set up this history is if I'm set up the boundary condition correctly. So it needs to be an abs and save boundary condition, absorb and save. It could be an accumulate boundary condition. So there's several different types of boundary conditions, but you do have to have the correct boundary condition set up. Okay, that concludes this video. In the next video, we will analyze the data and finish off with this series. And after you've watched the 5 videos that are part of this series, you should have a good handle on how to set up your own simulation. Thank you for watching.